So good morning, everyone. I am very excited to be sharing stage with aerospace safety expert in this beautiful city. Thank you for the invitation, David. My name is Amin Shigani. I'm Cto of Sentient Science. Sentient is a software company, and I'll talk a little bit about it. We're based in New York, and we have offices in Spain and in China as of recently. I lead an organization called the Digital Clone Platform organization within the company. My team has three different groups: a material science group, a data and analytics group, and a software engineering group. And I've been with Sentient this is my second year. Prior to joining Sentient, I've spent over 5 years at GE, building remote monitoring and diagnostic solutions, IoT solutions for GE Aviation, for GE Transportation, and GE Energy business units. I spent the formative year of my career building solutions for the U.S., for large-scale systems for U.S. government contracts. Most notably, before I left, I was the architect of the integration strategy for deploying emergency alert system nationwide in 2012. If you've been in the U.S., it is the platform through which we Americans receive weather alerts, amber alerts, and presidential alerts during an emergency. But today, I'm here to represent my material science group and talk about the extensive work that Sentient has done in computational component reliability. Given my background as mostly a systems engineer and a software technologist, I'll focus on our unique end-to-end approach to computational component reliability and the set of technologies we've built in support of this approach. So here we go. So since the 1980s, HUMS implementations have become an important part of managing the safety and availability of rotorcraft, mostly by providing the visibility into the actual health of the drivetrain components. HUMS implementations have a core capability, which is vibration-based diagnostics. However, vibration-based diagnostics and other sensing techniques can be difficult, complex, and sometimes ineffective, which means that we need alternatives, techniques, and methods for direct sensing of damage signatures in components. And one such alternative for direct sensing of damage signature is health estimation through component usage tracking, where inputs such as torques, speeds, durations, and flight regimes, we can use this input to estimate the amount of the useful life that has been consumed of those components. Traditionally, in the industry, physical testing is the preferred method by which models of damage evolutions are created. However, we know that physical testing can be time-consuming, and it's complicated and expensive to replicate the operational conditions with enough fidelity and coverage. So what is such an alternative approach? And this is what I want to present to you guys today. So at Sentient, our work is foundationally built upon the premise that critical drivetrain components fail when the materials that comprise them fail. So with this mindset, Sentient has adopted and developed a computational material science-based approach for predicting the reliability of components, and we did that in different applications. And over the past 15 years, with funding and cooperation of the United States government and rotorcraft O&Ms, Sentient has built models for damage mechanics that compute the initiation and propagation of damage in especially gears and bearings. And I think the video is, hopefully it's working. On the bottom lower right corner is supposed to be a video that basically shows a simulation of a crack initiating subsurface and going all the way to the surface. So the video is not working there. So how did we implement such approach? And I'll talk in detail about it. I said Sentient is a software company, and as a software company, we have packaged all the capabilities we've built over the past 15 years, the process, the tools, the models, the UI or the user interfaces into a single platform called Digital Clone Platform. And shown in this slide is the technology approach that we've taken to computationally measure component reliability at different scales. And it's decomposed into 6 steps, and I'll describe each of the steps. So for step 1, we do 2 things. We conduct a system level or drivetrain level multi-body dynamic simulation to compute the macro loads on the drivetrain components. And we follow that by a detailed analysis of the contact pressure analysis for bearings and gears, or at the interfaces of those components. So 2 things that we do. And the reason we do this is so we can understand the hot spots within the drivetrains. The second step, we conduct material characterizations of the contact hotspots to compute or to develop a computational model for that material. And this step basically involves reverse engineering of the material properties from an actual component sample, preferably a failed sample in the field. So in step 3, we conduct a mixed ESL simulation to compute the surface tractions applied to that material. And those tractions are basically applied to the material in step 4 to understand the initiation and propagation of damage. So by bringing, so that's in step 4. By bringing everything together in step 5, the damage propagation that we evaluate, we evolve that in time or in cycles. We build a damage propagation models to identify the failure mode and the corresponding components alive to that. So in step 6, basically the last step is we repeat steps 2 to 5 to compute or computationally capture the variability in that material. And here we basically, the results are reliability curves for that material, for that component. And we at Sentient have taken this approach, and we have built our platform based on this six-step approach to enable us to assess the health of drivetrain components in the wind industry. And these drivetrain or these models or these digital clone models that we call them digital clone models help us have an understanding of drivetrain assemblies, so we can give insights into of those assemblies to operators. What would this process here, I think I've talked in the title of the slide, from design to digital twin, how can this be useful to a gearbox analyst or a gearbox designer during design time? So let's dig deeper into step 1 of the 6-step process. On the left, an analyst or a gearbox analyst or designer is able to conduct a transient, flexible, nonlinear, multi-body dynamic simulations, taking in models for bearing and gear components from an existing library that we have, and have with the ability to incorporate housing stiffness to accommodate for its impact on dynamics. And shown in the figure on the left here is a representation of a rotorcraft main gearbox. So the results of this simulation is then fed into a detailed contact analysis for bearings and for gears. So in the center, we show results of a bearing contact analysis. Such analysis produces, like we show here, I think the slides are not showing the dynamics of these are supposed to be videos, 3 videos. So I apologize for that. But in the center here, the top figure shows a visual representations of the contact pressures, or the contact pressure and the sliding velocities distributions. And I think that's what should be shown in there. And the bottom plots we show a time series of linear and rotational dynamic information in the center here. And for bearings, we currently are able to do analysis on different types of bearing, spherical, tapered, and cylindrical bearings. We have a library of these components, but most importantly, we want suppliers, component suppliers, and O&Ms to build their own component models and incorporate in this approach as we help operators better manage their fleets. On the right side, we show results of a detailed gear contact analysis. And the same way, such analysis produces visual representations of the contact pressure or the contact patterns. I think that's the plot on the top right. Contact patterns on the tooth flank, as well as plots of the contact pressure and the loading intensity distributions here. And we, as I said, we have packaged these capabilities and these models as a product. We call it Model Builder product, and it's available as a desktop applications for designers to use in their desktop, but also as a web versions to again share those models across the enterprise or even across the industry. Now, with the detailed contact analysis result that I've shown in the previous slide, we now have the information, and as I said, we can produce a lot of help during design time. We have the required information to conduct simulations for the in-service behavior of that material or that particular, how it will behave in service. So during component design, this allows us to explore the impact on component reliability by varying different design parameters or inputs. And those are examples: loading spectrum, macro and micro geometries, tolerances, different types of lubricants or different lubricant properties, material choice and quality, residual stress, surface finish quality. So varying these design inputs and see the behavior of the material and the components in the field. These factors collectively impact the key characteristics, or can impact key characteristics of the whole system being designed, component being designed. And that includes production costs, production schedule, operations and sustainment cost, platform availability, and system operating envelope. A couple of things we also show in this slide. The videos are not working, it looks like, but on the top, on the left side here, we're showing an example of a traction analysis simulation. We're seeing the impact of contact on the surface finish of the components. And at the bottom, we show 2 different graphs representing some of the published work that we have done in the space here, especially work related to the impact of steady-state power level on contact fatigue and bending fatigue. And I have a reference of some of the work we've done there. So let me pause here before I get into the slide and recap. So I've shared with you a computational framework that we've built that is rooted in material science to study and understand component reliability. I have dug deep into at least step 1 of that approach, where we study the macro loading on the components and the impact on the or the contact impact on the component interfaces. I've also shared how this could be used during design time by analysts and gearbox designers. But what I want to do to finish up is discuss how this can translate into in the space called digital twin-enabled operations, or a paradigm. So here, what we have is if we are able, or by having a computational framework for component reliability, rooted in an understanding of the material science of the different components, we can generate many data points that can complement physical tests. And these computation models can then be used as the foundation for a digital twin for that asset, a digital twin for the rotorcraft. And we can use that digital twin for many applications for operations and sustainment. So specifically with the technology we've built and the tools that we've built, the computational tools can be used to generate, I think on the left here, SN curves for the components. These SN curves, from a practical perspective, can be translated into surface response models, packaged as what we call functional mock-up units for purposes of interoperability of those models and IP security for those models. And these FMUs then become the basis for basically being integrated in different applications with HUMS, with flight data monitoring, and other maintenance record to have a clear visibility into the health of the installed components. So at Sentient, we have implemented this approach in a digital clone platform for assessing the health of wind turbine gearboxes, and for also recommending asset action that could extend the life of those gearboxes. And currently, our platform, we have over 20,000 wind turbines under management. And in our contract base, we have over 40,000 assets that we are basically onboarding into the system bit by bit. So in summary, I think it is very critical that we continue to look at the limitations of physical testing, of HUMS implementation based on vibration-based techniques, and start looking at how we can have a computational framework that could supplement and augment what we do for component reliability and for addressing different damage mechanics. And I've tried to present one such approach and one such implementation of this approach. This capability is clearly very helpful during design exploration, is helpful for root cause analysis, and it's also helpful for supplier qualification and comparison. What we call digital clones are basically a foundational models that can be used to support and to advance a digital thread-based operations and sustainment paradigm in the aerospace industry. So I think with that, I'll give it back to David and take some questions.
I think we'll take the questions afterwards, after the presentation.
I'm fine with that. Okay. You want to do it after presentation or after all the presentations?
After the first session, so there are 2 remaining presentations, and then you have
all right, sounds good.
So thank you, Amin.